when you say control, we are looking at the manipulator in terms of its dynamics, which means that how did we come up with the dynamics of the manipulator? We did this. We took the Lagrangian, took the partial TL dq dot minus TL dq equals the torque. And then I said that this will give you AX equals B, where X is Q dot or theta dot. And then we really never really thought too much about this. We just said, that's the equation. We basically simulated the system like a double pendulum. It shows chaotic effect and so on. But now we'll sort of focus more on this A and B terms because they are very vital in order to control the system. So this equation looks something like this. M Q, what do we call this? Q double dot. Q double dot plus C Q Q dot plus G Q. Missing something here. Q dot plus G of Q equals tau. Okay, so here we can also write this if you want as Q double dot equals tau minus CQ Q dot plus minus G of Q, where clearly this is A and this was E and this was X. Okay, here, if you read any book or any paper on manipulator control, you will see that equation always. And then you should know what those terms mean. Here, MQ is the matrix which has mass inertia. Okay, it's only going to be a function of Q, which is the angles, not going to be a function of velocities. Okay, that's just because this form of the Lagrangian. Because the way Lagrangian is kinetic and potential energy, M is always a function of Q or positions. CQ Q dot times Q dot is the centripetal Coriolis, let's say acceleration slash torque. Okay, it's always, well, it's in the form that you can write it as C times Q dot, where Q dot is the velocity of the joints, and then GQ is the gravitational torque. So it's the torque which is needed in order to hold the manipulator in static equilibrium. So when you did this calculation of using the Jacobians, you can actually use the Jacobian transpose times mass times gravity to get that GQ. And then the tau is external torque. Now, if you have torque due to friction, torque due to viscous forces, all those torques will come in that torque. So you will then write it as sum of torques external to the system, which would be gravity, dissipation, or some actuator torque, like a motor torque. So what I'll do is I'll sort of build intuition towards how to, what sort of problems arise in control. One of the the two important problems we'll study. One is, given a pendulum, can you get it to stick to a given set point. So let's say that there's a two-link pendulum and you want it to be upright, and there's some disturbance which is pushing the pendulum. Can it still remain upright? So that's the set point control. The other problem is trajectory control, which is, let's say now you want a manipulator to draw some, say, figure 8 or angles to trace some trajectory as a function of time. Can you do that? And that will be a trajectory generation problem. So those are the two things we'll be focusing on. Set point control. P is trajectory controls. So let's look at a simple example. We said there's a equation which looks like this. Okay. What we'll do is we'll look at the simplest form. So m q double dot. So I just made the mass as constant. Assume c q q dot is, again, c is constant. And g is, let's replace that with k, and you'll see why. K times q equals, so it's k times q because it's sort of some function of position. Okay, I don't know if you realize this, but this is actually same as a model of a spring mass damper system. So if you have a spring and a damper, attached to a mass, mass, spring, damper. So you can see that this is the damping term, this is the spring term, and then this is the mass, and then this torque. I just keep it as torque, but usually people write F for force. Okay, so I think that the intuition we'll get from this simple system can just be extended to control n degree of freedom system, and you'll see how that is done. So let's take this spring mass damper system, and this will be sort of a review, and then we'll come to this point where we are doing complex systems. Let's rewrite this as q double dot plus c divided by m q dot plus k divided by m q equals tau divided by m. For a moment, let's just assume that this is 0. That is, it is a free vibration system. There is no external force. Okay, now if you remember, the way you analyze the system is you redefine, you define what is known as a damping term. The damping constant is defined as, first let's define the natural frequency. It is square root of k divided by m. And then 2 damping times omega n is c divided by m. So there is, so it's like this. You have two constants. Well, there is 3 constants there, k, c, and m. But because of the way this equation is, it really depends on 2 numbers. That ratio in front of q dot and the ratio before q. So you're allowed to replace one set of constants with another set of constants. That's why you just made this choice, because there's a intuitive meaning to this choice. Omega n is the natural frequency. If there's no damping, then it's the frequency at which this mass will vibrate. The damping terms, I think it's called zeta. Zeta will give you how fast the energy is dissipated in the system. And so this is the usual choice when you look at vibrations of systems. Okay, now you can actually solve for the damping. It is T divided by 2 square root of mk. Okay, so here's one thing which you should remember, and the other one is the damping. Now, if you remember, the way this system is analyzed is for different dampings, you get different response. Okay, so there is for that particular equation, you can actually solve for Q as a function of time by, how do you do that? I think you assume the solution to be A sine omega t plus phi, and then you substitute there, and then you solve for the amplitude and the frequency, and then you get an answer. That's one way of doing it. Another way of doing it is to just simulate the system and you'll get a response. Okay, so depending on the damping, there are 3 cases. If the damping is greater than 1, okay, remember that the damping is C divided by 2mk. So if the damping is greater than 1, which means that C is greater than 2 square root of mk, this is called an overdamped case. The damping is equal to 1, which means C equals 2 square root of mk. It is critically damped. And third is when theta is less than 1 and C is less than 2 square root mk. This is underdamped. Okay, what it means physically for the pendulum is if you take the mass and you set it away from its 0 equilibrium position. Let's say here, if it's underdamped, you'll see that it oscillates, and eventually things die out. If you make it overdamped, then it will die out very slowly. And then if you make it critically damped, then it will die out sort of faster than either of those. So the red and the green eventually die out, but they take a whole lot of time than the blue. So let's name these. This is damping greater than 1. This is damping less than 1. And this is, okay, so this is Q, this is T. This is the start, which is different from 0. And so the thing is, if you are looking at a set point control or even trajectory tracking, imagine the pendulum is vertical. Now you perturb the pendulum from its vertical position to some angle, and you want to get it back to 0, right? Which of those 3 profiles you'll choose? Well, you'll use the blue one because that gets you to the 0 point the fastest. Okay, so that's the preferred one. So fastest decay to 0. Okay, that's one good thing. The other good thing about that profile is that it doesn't show unnecessary oscillations. So the red is unnecessary oscillations. It goes from 0.5, it will go to minus 0.3, then plus 0.2, then minus 0.1, and so on. And you don't want that. Many systems, you cannot have that response go on the other side. So that's a good thing that it is not showing that, but it's also, unlike the green one, which also doesn't show the oscillations, it dies down faster. So the goal of control, at least the way we think about it, is our goal is to take any system and get it to 0 as fast as possible, okay, without oscillations. Okay, so How do we do this? Okay, so we will use the torque or force or torque to achieve E equals 1, which or theta equals 1 to achieve fastest Okay, so now what I mean by this, well, if you're given a system with a spring mass damper and you don't have any control over the torques, you let it go, there's no guarantee that it will be critically damped because it just depends on the system parameters, right? So for example, here it depends on C, M, and K. If the C, M, K don't follow this relation, then it will not be critically damped. But you have, to your benefit, you have access to the torque now, and that will help us. So let's see how to do that. So let's say that this is our system. And it is not critically damped. So what we'll do is we'll create a controller which will take care of this. So we'll assume that, let's just divide out, just keep it this way. Let's just write torque as Kp. So torque is minus Kp Q minus Kd Q dot. So this is called a proportional control. So it's proportional to Q, and this is derivative control. Okay, this is often known as PD control. Okay, so let's sub that in the first equation. Okay, so we have MQ double dot plus CQ dot plus KQ equals minus KPQ minus KDQ dot. Okay, let's move things around. C plus KD Q dot plus K plus KPQ equals 0. Okay, so another thing to remember is you have full control over what torques you supply to the system. So this is chosen by the designer. You can choose any KP, KD you want. Okay, so now we said that for the system to be critically damped, the relation is C equals 2 square root mk, where C is the term in front of the damping, or the velocity, and K is the term in front of Q. So we can write this condition over here. It's C plus KD equals 2 square root M K plus KP. So this is critically damped. Okay, now what we can do is we can solve for, let's say, KD. Okay, so what we do is we square both sides. MK plus 2MP. We can write K E square plus 2 AD times C plus C square minus 2M A minus 2M. Okay, so you can recognize that's a quadratic equation in KD. So we can solve for KD. There's an analytical solution, right? solve for KD. KD is, I'm just using that formula for quadratic equations. So solution for quadratic equation 2 square 4 a times okay. So after you simplify this, you get KD equals minus C plus or minus 2 square root K plus KP. Okay, so you see that there are two roots which you get for a quadratic equation. Now the thing about using the, well, which root will you use? Well, if you use the one which has the negative sign, so minus C minus 2 square root, you'll see that the KD is negative. And the thing about feedback control is if you feed back a negative quantity, then you will see that it's not the traditional feedback, it's going to give positive feedback, which means instead of dying out, the amplitude will keep growing. So we have to ignore the negative one. So the solution is choose stable gain. So the stable one is KD equals minus C plus 2 square root A plus KPN. Okay, note that we have choice over two numbers, KP, KD, designer's choice. So you have two numbers you can tune, but there's only one condition on KP, KD, which ensures that you get critically damped systems. So what you do is you fix one to whatever you want, and then choose the other one based on this condition. So if you choose KP equals say 100, then you put the value of 100 and then choose KD, and that's what you typically do. There's nothing stopping you from putting KP equals 1,000,000 or more than that. But what happens in real life is that this kind of control works well only when the system has little or no noise. The moment the system has noise, by noise I mean that your velocity or the position measurements would not be exactly what it is, but it will be, it'll have some, would sort of say caution or some noise, which means that it will be off. And once it is off, let's say it's off by 0.01. If you make a gain of 1,000,000 and you multiply with 0.01, it'll still be a huge number. That's like 1,000, right? And that part will make the system go unstable. And so you do not want to have high gains. So typically the bigger the gains are, the better control you get, but then they also amplify noise. So when you tune these gains, you're sort of fighting between how good a feedback you want, how much you want it to settle to zero, versus how much noise is there in the system. Okay, so I have an example of this. It's very simple in terms of its coding because you just have a single spring mass damper, MCK, a mass C and K is 1. And what I've done here is I've simulated the original system, which has equations minus Kx minus K dot. This should be C, right? So C is the damping. So this is the system parameters, and this is my controller. Okay, the controller is again based on that formula I wrote earlier. Okay, so if you run this, and what I've done here is I try to get the system starts at 0.5 with a 0 speed, and so clearly the goal is to go to 0. So if I run this, okay, that's the response. You can see that it is basically sort of under damped because it shoots beyond 0, and there's a slight oscillation, and then it goes to 0. So there is this is under damped system. So then we want to now take the system and control it such that it is critically damped. What you do is you choose KP, KD. Here KP was chosen to be 10, KD is a function of KP, that formula which I wrote down. And so I'm just going to comment this out, uncomment this line. And now if you run this, we see that it's critically damped because you get to 0 in the fastest time. Well, if it's not fast, you can try other games. You see that it won't really come back to 0 in the fastest time. It takes about little less than 2.5 seconds to damp out. If you increase this gain, KP, which is the only free parameter, you see the response becomes faster and faster. So remember, it was about little less than 2.5. Now you see it's less than 1 second, whatever units I have there. Okay, so it's clearly doing its job when you change the KP and KD, so that follows that formula. Okay, so this is